thanks so much for inviting me, for thinking of me for this event. Thank you so much to the organizers, especially to Christian Stumpf for being so accommodating and allowing me to give this talk online. I would rather have given it in person, but anyway, this time it's not the case. But anyway, I hope that I can give something to each of you, and please feel free to interrupt me every time you feel like. So let me tell you or give you an overview of what I'm gonna talk to you about. So I'll just minimize this a little bit. Okay. So this is an overview of the results I'm gonna share with you. So I will tell you a very nice interaction between these combinatorial objects. So here in the upper right corner, you see the permutahedron. And in this tiny picture, you see that it has been split, it has been subdivided. It has been subdivided via two hyperplanes, if you wish. And that subdivision with these two hyperplanes has made the permutahedron to be split in 4 pieces. And each one of these pieces, you see that actually is kind of, say, labeled by a sequence of these objects that we will define. They are lattice path matroids. And these are the kind of subdivisions I want to tell you. I will tell you about what lattice path matroids are if you're not familiar with them. What do I mean by this chain of lattice path matroids? How do they correspond to subdivisions of the permutahedron? What are these hyperplanes that induce those subdivisions? And also, how we can think of these subdivisions as being realized by points. Here, this subdivision in particular is realized by a tuple in R14, and that tuple satisfies certain non-negativity conditions that define the non-negative tropical black variety. So there are lots of words there, but basically it's an interaction between these kind of objects, okay? Okay, so let me start with some basic definitions. So let's just think of a matroid as being a pair consisting of the ground set, that for me, bracket n, denotes the finite set 1 up to n, and a collection B, that we will refer to them as bases, that satisfies a certain exchange condition that you can see here. And so I will illustrate the definition with the following example, but just some terminology that we will be using throughout. So the collection B, I will refer to them as the bases of the matroid, and one can show that any of its elements have the same size, and that size is going to be the rank of the matroid. So the first and main example for my talk will be lattice path matroids. So they were defined as we know them by Bonin, Demier, and Noe in a paper in 2002, although they also appear somehow in earlier work of Stanley. And so let me give you one way of thinking of them. So I'll define a matroid, and for that I need to give you first a ground set. So let me think of the ground set consisting of 1 up to 19. And what I'll do is imagine I draw a grid from the origin to another point such that the total number of east and north steps is 19. So here, this grid has width 11 and height 8, and the total number of steps is 19. And now I need to tell you what is the collection of bases according to this definition to illustrate it. And actually, so the total number of north steps, it will constitute the rank of the matrix. So once I have set up my grid, I will throw in a lattice path. So this is just a path from one corner to the other, from the origin to the other point. And I will just walk north or east steps of unit length 1. And this lattice path in particular is going to represent one of the bases of my matroid. So in this example, I told you that 8 will constitute the rank of the matroid. And it means that each basis will be a subset of size 8 out of 19. And so here my 8th tuple will be, you can see the labels of the north steps. So here I just care about, every time I draw my lattice path, I just care about at what point did I go north. And so those are my labels. The labels indicate to me at what time did I go north, okay? So I drew one lattice path that I chose, and I will do another one with the only restriction that the other one I draw is going to be weakly below this purple one, graphically. So here, let's throw this one in, and I have drawn two of them. I'm calling U the purple one just because it's upper. So over here, we have thrown in two lattice paths, and I just make sure that the one that I'm calling U is above the one I'm calling L. And with these two, I will be able to give away my whole matrix. So to illustrate the definition I have given, these two are bases of my matrix, and the definition tells me that I should be able to exchange an element from U with an element from L and obtain again a basis. So let me, for instance, interchange or exchange the element 1 from U with the element 8 from L. And that means that I will keep all the remaining labels of U, all of them except one, and I will throw in 8. And when I do that, what I get is this collection of north steps that actually gives me a basis. And what will be all of them? All of them will be actually, graphically, it's going to be every lattice path that goes from the origin to the other corner that is in between U and L, does not leave that region. And also you can think of it as being this an 8 tuple. You will be able to obtain a basis if component-wise, the label from that set B is in between the corresponding label of U and L. That's going to be my collection of bases, okay? Is that okay? That's going to be the set of bases, the collection of bases we will use throughout, so let me know if it's not clear, okay? Okay. Actually, this family of bases corresponds to certain types of matrices that we will focus on. So let me look at the linear algebra of matrices for a second. So let's think of everything we're going to be here is going to be over the reals. So my definitions will be all based on the real numbers as my base field. So I will say that the Grassmannian Kn is given by vector spaces of dimension k in Rn. And if we were to choose one such vector space, and if you fix a basis for it, so a basis is going to be k vectors in Rn, and say you arrange them in a matrix, if you do that, then you are going to obtain a full rank matrix of size k by n. And out of that matrix, you will be able to define a matrix. And the way you can do that is you have n columns in your matrix, and just look at what k tuples of those columns have non-zero determinant. So what are the maximal minors that are not zero? So in other words, what set of columns satisfy that the corresponding Proctor coordinate or determinant is not zero? And those k tuples of subsets of the columns will give you a set of bases for a matrix. And so we're going to say that if you have a matrix, an abstract matrix over the set N, we're going to say it is representable if you are actually able to come up with a matrix that represents it in the sense we just said. And so let me give you here an example. Say you take this matrix. This matrix is a lattice path matrix. It's a lattice path matrix whose path U is 1 to 4, whose path L is 4, 5, 6. It's a matrix on 6 elements. And if you look at this picture for a second, you see that every subset of size 3 of your set 1 up to 6 is a basis, except for the set 1 to 3. Everybody is a basis except that one. And this matrix is actually representable. And being representable means that you should be able to find a matrix of rank 3 on 6 elements, such that every column, every subset of the columns of size 3 is linearly independent, except for columns 1 to 3. And so, for instance, you could think of this matrix right here, where the stars are just generic elements. If you choose them generically, you are guaranteed exactly what I just said, that every triple of columns, except 1 to 3, will correspond to a basis. And it's a fact that along these lines, you can actually demonstrate that any lattice path matrix is representable. If you're familiar with the terminology, what this is saying is just that lattice path matrices correspond to generic points in the Richardson cell decomposition of the Grassmanni. But it doesn't matter if you're not familiar with it. Just keep in mind that lattice path matrices are representable. Okay. And actually, they are not only representable in the way that we just defined, but actually they're representable non-negatively. So let me go into that now. So say we're going to refer to as, or we will say that the non-negative Grassmannian, Kn, is going to consist of all the K by N matrices, if you want, full rank, that satisfy that its maximum minors are non-negative. So you impose a non-negative condition there. And we will say that positroids are those matrices that are representable with this non-negativity condition. So positroids appear as we know them in work of Posnikov from 2006, although they also have some early appearance in the work of Bloom under the name of base-sortable matrices. But we'll think of these positroids as being defined in this case. And so let me give you a couple of examples. So say you have here a matrix on the ground set 1 up to 4. It's a matrix of rank 2. And actually, I'm giving you a representation of that matrix where A and B are some real numbers, non-zero real numbers. And I want to know if I can conclude this matrix is a positroid. So according to the definition, I should check that these maximum minors indexed by this by the columns 1, 3, 1, 4, 2, 3, and 2, 4 are positive, and the other ones are 0. And if I look at this little example, I will check that all I need is for B and A to be positive, which is possible. So I could certainly come up with lots of ways of realizing this matrix as a positroid. On the other hand, if we were to look at this one over here, this is also a matrix. And if I would like to know whether it's or not a positroid, I would have to check again the same non-negative condition, but now for this set of columns. And if you run through the conditions, you will check that you will need, on one hand, B to be positive, so that column 1, 4 has positive determinant, A to be negative, if we want this non-negative condition, and on the other hand, A to be positive. So it's not possible. So although this matrix is representable, it's not a positroid. And if you look a little bit or compare these two matrices, you will see that the only difference is that the roles of label 2 and 3 of the ground set are changed. So if you want, the ground set of one is a permutation of the other. What this says is that positroids rely very strongly on the labels of the ground set. So that's a big difference with matrix. So actually, so I got interested into lattice path matrices because they actually happen to be positroids. I'll say about that in a second. But I usually, when I think of positroids, I don't think of them in terms of realizing them via a matrix that has this non-negative condition, but other ways. So let me tell you a couple more ways you can think of positroids. So let's compare them geometrically, the matrix. So one way you can differentiate matroids with positroids is via via polytopes as follows. So say you have any matroid. If you have any matroid, regardless whether it's representable or not, you can define its matroid polytope. And what you do is that you have your collection of bases, and for each basis, you will only take the vector, a 0, 1 vector, that is given by the indicator vector of that basis, and you take its convex hull. If your matroid is a matroid over the set 1 up to n, you are going to obtain a polytope in Rn. And actually, so let me give you here an example. So one of the, say, the key examples in matroid polytopes is that of the hypersimplex. So where does the hypersimplex arise from? The hypersimplex arises, if you want, as the matroid polytope of what I'm denoting here as the uniform matroid. So for me, the uniform matroid Kn is the matroid on the ground set N, such that every subset of size K is a basis. And the uniform matroid is actually a lattice path matroid, corresponding to the diagram of a full grid. And so here you see illustrated the uniform matroid 1, 4, and here the uniform matroid 2, 4. And actually, if you were to, because of the very definition of the uniform matroid, if you were, for instance, to want to illustrate a matroid polytope of another matroid on the ground set 4 of rank 2, you will realize that actually the matroid polytope of any other matroid of rank 2 over 4 is going to be a subpolytope of this one. So for instance, if you were to take this matroid of rank 2 on 4, its matroid polytope will have as vertices a subset of the hypersimplex 2,4, and actually it's going to be just this one, because you are only getting rid of one vertex compared to the left one. Okay, so not only you can define or you can associate to every matroid a polytope in this way, but actually Gelfand, Goreski, McPherson, Serganova showed that this is another way of defining matrices. So what this means is that every time you have a polytope whose vertices are 0, 1 tuples, then the corresponding subsets they came from are the collection of bases of a matroid if and only if the edges of your polytope have directions ei minus ej. And if you are familiar with generalized permutahedra, all this is saying is that matroid polytopes are 0, 1 polytopes that are generalized permutahedra. This edge direction condition means it's a generalized permutahedra. And so that's one way of thinking of matroids. And actually, there is a similar way of thinking of positroids. So in work of Ardila, Rincon, and Williams, it is shown that positroids are matroid polytopes. Positroids polytopes are matroids that happen to be alcoved. And what alcove means is that if you are able to give a hyperplane description of your polytope, the inequalities you see will be of this kind. So it's like consecutive, sum of consecutive xi defining the hyperplane description of your polytope. And so an application of this is that LPMs already have a very well-known hyperplane description. And that hyperplane description, I'm not going to go into details, but basically the hyperplane description given by Nawa, Martinez, and Ramirez tells you this is an alcove description, and that says that LPMs are positroids. And certainly there are other ways of proving they are positroids, but this is one of them. And just as a side note, if you're familiar with the Hart theory, a very cool thing of knowing that your polytopic alcove is that actually you can endow it automatically with a regular unimodular triangulation. Okay, so lattice path matrix, bottom line, they are positroids. And so this is one way of thinking of them geometrically. And there are other combinatorial ways of thinking of them. So let me present them to you. So let me run this example. So basically, via this example, I will tell you what is an alternative to distinguish matroids from positroids. So what I'll do is I have a matroid. In this case, I have again a matroid on the ground set 4 of rank 2. And here I'm giving you the bases, all the bases of the matroid. What I'll do is I'll construct a combinatorial object that I'll call the Grossman necklace. And what is this going to be? Since my matroid is a matroid on 4 elements, so I will provide a sequence of 4 subsets, and each subset will be just defined by what is the smallest basis according either to the total order 1, 2, 3, 4, or 2, 3, 4, 1, or each one of these total orders. So taking your collection of bases, then you just take the minimal of them according to each one of these linear orderings. And what you get is this. So for I1, this is the smallest basis. For I2, this is the 1. For I3 is these bases, and you see there is repetitions, that's okay. But the point is, from your collection of bases, here you are taking a subset of them. And this subset of the basis is enough to tell you if your original matroid is or not a positroid. So what do you do now? Once you have constructed your Grossman necklace, you ask yourself, okay, who else or what am I going to construct now? I'm going to construct the envelope given by this necklace. And the envelope tells you, now what you will do is you will grab every other subset of size 2 that is bigger than or equal to every of the elements of the Grossman necklace according to each one of these linear orders. So for instance, the subset 2,4 passes the test because it's bigger than or equal to each one of the I sub j's according to the given order. It means that 2,4 is part of the envelope of the envelope that we are constructing. And for instance, if you were to check the subset 1,2, 1,2 will not pass the test because 1,2 is not bigger than 1,3. And similarly, 3,4 does not pass the test because it's not bigger than 3,1. What this says is that the envelope actually, in this case, coincides with the set of bases of your matrix. When the envelope coincides with the collection of bases, it means your matrix is a positroid. In general, what happens is that the collection of bases is properly contained in the envelope when your matrix is not a positroid. So anyway, here you have your Grossman necklace from this, and actually you can also associate another combinatorial object to it, which is called a decorated permutation. So a decorated permutation is just a permutation on the set 1 up to n, and the decoration is just an overline or an underline that you put to the fixed points of your permutation. If you are familiar with the terminology, the fixed points, the decoration, when the decoration is overline, it just means that you have a co-loop, and if it's underline, it just means you have a loop. In this case, my matrix does not have any of them, so that's why the decorated permutation does not have any of it. And you can obtain the decorated permutation out of the Grossman necklace. That's not too relevant right now. The point is that if you were to grab all the decorated permutations on a fixed ground set, you actually are describing all the positroids on that ground set. It's a bijective correspondence, and there are other objects, and all of this is work of Postnikov. There are many it's very rich combinatorially, the class of positroids, and that's what attracted me in principle. So I started thinking of positroids in terms of decorated permutations, and here you have a picture of all the decorated permutations on the ground set 3. And I have here ordered them partially somehow. I will tell you how they are ordered in this example. Basically, here you have positroid of rank 0 on 3 elements, rank 1, rank 2, and rank 3. So how are they ordered? They are ordered using the notion of flag matrix. So one way of thinking of flag matrix is this. Say here you have a representable matrix. So here you have a representable matrix given by this matrix. It's going to be a representable matrix of rank 4 on 7 elements. And what I'll do is I'll define circuits of the matrix. So what are they going to be? Basically, you're going to grab the subsets of the columns that are dependent but minimally. So for instance, in this case, if you were to take the column set 1, 2, 3, 1, 2, 3, you can see is linearly dependent, but minimally, in the sense that if you were to get rid of any of them, you are going to obtain a linearly independent set. So my circuits are the minimal dependent sets. So I do this with this one, and let me now consider this other matrix that I'm calling N, and take also its circuits. So at first sight, one thing you can observe in relation to these two matrices is that what I did really to construct N was just take the same matrix that represented M and deleted some of the bottom rows. I deleted the last top rows, the last two rows, and that's how I built N. And it so happens that if you would take every circuit of M, you will see that every circuit of M is union of circuits of N. So for instance, the circuit 1, 3, 4, 6 is union of 4 and 1, 3, 6. And that will happen with every circuit of M. So this particular example that we have built out of a representable matrix is one way of defining what being a flag matrix is. So basically, if you have two matrices, doesn't matter if you're representable or not, you have two matrices on the same ground set, then we're going to say that in this case, N is a quotient of M, if what we described just a second ago happened, namely every circuit of M is a circuit of N. And when that happens, we are going to denote this by this. So basically, this less than or equal to Q is kind of giving me a partial order on matrix on the same ground set. And that's how we're going to define flag matrix. So flag matrix are sequences of matrix that are related via this quotient relation, okay? And so the question I got very interested on when I started working with positroids, given the combinatorial richness, was precisely if you give me two positroids, say you give them to me as decorated permutations. Can I tell you whether one is a quotient of the other one just by reading of the permutations? So that's part of the work we did with Anastasia Chavez and Daniel Tamayo. And the picture I showed you a moment ago is precisely a poset on positroids where the order relation is N a quotient of M or not. So that's a quotient relation. And what we did is via the decorated permutation, determining or characterizing some of the quotients of a uniform matrix. We did this just by defining certain shifting operation in the decorated permutation. And as a side note, this shifting operation we define on decorated permutations appeared in later work of Parisi et al. In their study of tilings of the M=2 amplitude-hedron. Also, in this paper, given what we have done, we didn't manage to give a full characterization, but we did enough computer experimentation to be able to conjecture what should happen in general. And our conjecture was proved just recently in a paper by Chen et al. So one thing that happened in this work we did was that one problem we faced was, if you were to give me two positroids on the same ground set, and I know this positroid N is a quotient of this positroid M, say N has rank 3, say M has rank 11, whatever, doesn't matter. So can you actually give me a chain of positroids of ranks 4, 5, 6, up to 11, such that you have a full flag of positroids? In other words, if you want to think in terms of poset, can you always build this poset so that you get a graded poset? That's something I don't know yet the answer to. Although, if you, instead of thinking of positroids, you were think of matroids, the whole class of matroids, the answer is yes. But for positroids, I do not know the answer to that. I do not know the answer to that. And so the next thing, if you are not, if you are not able to solve something, so you try to soften the problem. And so that's how I got into studying lattice path flag matrix. So this problem, we were able to answer affirmatively with Collia. On one hand, we understand fully how to characterize quotients of lattice path matrix, and actually we can build a graded poset out of the quotient in relation in lattice path matrix. So let me give you an example of how this works. Here you have a lattice path matrix. This is a lattice path matrix of rank 8, and I will build a quotient of it of rank 1 less. And to do that, what I need to do is I need to delete a label from the purple and a label from the green. I cannot just pick any pair of labels I want. I have to satisfy certain conditions. And so what I'll do is, say, for instance, I want to delete label 11 from the top. If I want to delete label 11 from the top, I have now some choices to delete from the bottom. And the choices I have are the green labels that are in this region. So basically, every label in the top defines a region where from which you can take a label from the bottom. And in this case, say in the bottom, I choose to delete 8. So I will delete 11 and 8 and see what lattice path matrix I have. And when I do that, it means that in the last path matrix I get, where I keep all the other labels as they were, only 11 now is horizontal and only 8 now is horizontal. The rest are as they were before. You get a quotient and you can iterate this. So that's basically what guaranteed or allowed us to conclude that in lattice path matrix, you are able to build a poset that is graded. So here you have a comparison between, on the left-hand side is the poset of all positroids on rank 3, ordered by quotient. On the right-hand side, you have all lattice path matrix of rank 3, ordered by quotient. On the left, I have colored the positroids that are not LPMs, so that you see that the right-hand side is just a subposet of the left-hand side. In both cases, what you are considering is full flags. And full flags in the sense that you start from the positroid of rank 0, which is the uniform matrix 0n, and so on. And because in both cases you are considering positroids, so each flag has as constituent or is formed by matrices that are positroids, it means that each piece in the flag is can be represented as a point in the non-negative Grassmannian, is a positroid. But what really marks the difference between the right-hand side and the left-hand side is that the right-hand side not only every point is a positroid, but actually the full flag, every full flag in the right-hand side is a point in the non-negative flag variety. What does that mean? It means that if you were to take a full flag from here, that full flag can be obtained by a matrix of size n by n with positive determinant, such that if you were to take only the top I rows, you obtain a matrix that represents the ith positroid in your flag. So that's the big difference. Again, I want to point out that even though in the left-hand side, every flag is built out of positroids, it is not the case that you can always take a flag from here and cook up a matrix such that the top I rows give you a positroidal representation of the corresponding piece. That doesn't happen always on the left-hand side, but it happens always on the right-hand side. And how do we know that? We know that because we started studying flags of LPMs via polytopes. So how do you do that? What you do is you have your full flag, and if you take your flag, you know that for each matroid, you can just produce its matroid polytope. And once you have your full flag, so just take the Minkowski sum of it. If you don't know what the Minkowski sum of polytopes is, just think of this is a subset of R to the n. Each one of them is actually a subset of R to the n, and you're just taking like the sum of elements from one to the other. So that's how you can define the flag matroid polytope. And here, on the left-hand side is again the poset of lattice path flag matrix. On the right-hand side, here you have this full flag. This full flag is this flag from here, only that I am ignoring the bottom and the top element because it's the same for everyone. So in the right-hand side, you can see the polytope corresponding to each one of the full flags. And it happens that when you have a full flag of matrix in general, and you construct its flag matroid polytope, you always get a polytope whose vertices are permutations. So in this case, because I'm considering full flags, I'm obtaining polytopes whose vertices are permutations on the set 1 up to 3. And the reason we know that each one of these full flags is a point in the non-negative flag variety is because there is a bijective correspondence between points in the non-negative flag variety, full flag variety, and intervals in the Bruja order. This is work of Lauren Williams and co-authors of her. And so in this case, we managed to prove that every polytope that comes from a full flag of lattice paths is an interval in the Bruja order. And because it's an interval in the Bruja order, the result above tells you then that it's a point in the non-negative flag variety. And again, what this means is that each one of these full flags can be thought of as coming from a matrix in which the top I rows represent a positroid. But we did this via the polytopal perspective. And actually, one thing that we observed in here was that in this example in particular, and other examples we were looking at with Collier, is that, so say, for instance, I'm taking these two full flags. This flag has as corresponding polytope this one here. This flag has as corresponding polytope this one here. And actually, well, this example is small enough, but as I said, testing with other examples, we kind of wonder if we could actually cook up a subdivision of the permutahedron into pieces such that each piece is the flag polytope of a lattice path of flags. And at that point in a parallel project, we were working with regular subdivisions of LPMs. So actually we wanted to know if this subdivisions were regular, in the sense that if you were to associate heights to the vertices of a polytope and you look at the lower hull, that subdivision you have above corresponds to that association of heights to the vertices. So let's do a parallel, or why we thought that should be the case. So in the case of the hypersimplex, we already know this is the polytope corresponding to the uniform matrid Kn. And so there is, here is the hypersimplex 2,4. And so there is a result of Lukovsky, Parisi, and Williams that tells you that actually, on one hand, you can, if you are able to subdivide the hypersimplex in such a case that, for instance, in the left-hand side here, you have a subdivision of the hypersimplex. Each piece is a positroid. On the right-hand side, you have a subdivision of the hypersimplex, and each piece is also a positroid. In both cases, the result tells you that here, this subdivision is regular, namely, it comes from associating a height to each of the vertices, and that height is a tuple. And actually, that tuple satisfies certain non-negative conditions. I'm not going to give the definition here, but basically that you are able to associate a height to the vertices, and that height vector is a vector that satisfies the conditions for being a point in the non-negative tropical Grassmannian. And basically, that's part of the result, that subdivisions into positroids of the hypersimplex correspond to points, or can be thought of as points in the non-negative tropical Grassmannian, and vice versa. A point in the non-negative tropical Grassmannian can be thought of as a height to the vertices of the hypersimplices and give you a positroidal subdivision. So these are the only two positroidal subdivisions of the hypersimplex, and one of them is a subdivision that is purely in terms of LPMs. And so actually, subdivisions of the hypersimplex in terms of LPMs had been studied before by Chatelain and Ramirez, and recently by Devari and Ashraf. And so we wanted a similar story for the permutahedron. So the permutahedron, you can, in parallel, as the hypersimplex, the permutahedron, you can think of it as the polytope coming from the full flag, where each constituent is the uniform matrid of every rank. And so recent results, on one hand by Josvik et al. And Boretsky et al., tells you that something similar happens. So if so on one hand, you actually can obtain subdivisions of the permutahedron into pieces that are Bruch interval polytopes, and actually those subdivisions are regular, and are regular in a special way. So you can realize them as points in the non-negative tropical flag variety. And so what we wanted to know is, in parallel to the hypersimplex story, is, are there subdivisions of the permutahedron into flags of lattice path matrix? And the answer is yes. So let me show you how this works. So here is, you have three examples. Each one is giving you a subdivision of the permutahedron. And in each case, every subdivision is a subdivision into two pieces that actually correspond to cutting the permutahedron via a hyperplane. I will tell you what they are. And actually, in each case, you obtain that each piece is an interval. Being an interval already tells you it's a flag of positroids, but moreover, every interval is a flag of LPMs. If you were to consider the common, say, refinement of these subdivisions, you obtain this thing here into 5 pieces, and each piece is also a subdivision of the permutahedron corresponding to a lattice path flag matrix. So we were after understanding the finest subdivisions of the permutahedron into pieces that are lattice path flag matrix. And instead of understanding the finest, then we turned into, let's understand the coarsest ones, like these ones, the coarsest non-trivial ones. So let me show you here the example. Illustrate this theorem with the example. Basically, one of our most recent results from a couple of months ago tells you that actually you can build coarsest subdivisions of the permutahedron into pieces that are LPFMs, lattice path flag matrix, with certain types of hyperplanes. There is a type of hyperplane that, as in the example n equal here illustrates, comes from hyperplanes of this kind, x1 equal either 2, 3, 5, or x5 equal 2, 3, 4, or this other type of hyperplanes, x1 plus x2, or x4 plus x5 equal 4 or 8 in this case. And basically, what we did was, via experimentation, noticing that these hyperplanes cut, each one of these hyperplanes cut the permutahedron into two pieces, and each piece can be easily described as an interval, and we interpret that interval in terms of LPMs because we understand well quotients of LPMs. So that's basically how we do it. So these coarsest subdivisions of the permutahedron came from the fact of understanding well LPFMs. And so here you see for n equal 4, these are in the bottom, the coarsest subdivisions of the permutahedron. And what this is doing is, if you were to take a couple of these subdivisions, which ones produce you again a subdivision into pieces that are LPFMs and so on. And so you see in the top, there are these other two that are the finest of them all. And in this picture is actually kind of symmetric, and that's another thing we proved. There is some sort of duality that you can play with, and basically tells you that every time you have a subdivision into LPFMs, you can construct a dual one. And just to finish, because this is so very current work we are doing, we have several things we want to do, several questions to share with you. So one of them is, you saw that in the coarsest subdivisions, we have two types of hyperplanes, basically. So with the hyperplanes of type x1 or xn equals something, if that gives you a subdivision of the permutahedron n, and actually what you can do is, with that subdivision, you can think of it as producing a subdivision for the permutahedron n minus 1 by doing deletion on the matrix involved. And so we want to know if for the other type of hyperplane, so the hyperplane of type xi plus xj, you can actually define an operation on the matrix that allow you to produce subdivisions either from the permutahedron n minus 1 or n plus 1. And then we have some further questions. We understand these coarsest subdivisions, but we want to understand which ones of them are compatible. So if you have many of these coarsest ones, which ones give, after using them simultaneously, produce you a subdivision of the permutahedron. We also want to know what are the finest subdivisions of the permutahedron into lattice path flag matrix, what are their effectors, and we know by the theory that these subdivisions are regular and correspond to points that are part of the non-negative tropical flag variety, but we do not know yet how to realize them in that sense. So here you can see this is extracted from a paper of Boretsky, Error, and Williams, where they do computations for the permutahedron before and subdivisions of it. So here you can see these are all the coarsest subdivisions of the permutahedron before into flags of positroids. And these 6 are the 6 I showed you, the coarsest ones for the permutahedron before. You see that their vector produces the coarse species. And we would like to understand this in general too. And so these are some of the questions we are working on right now. But also, if you want to try some of them, you can ask me. And just this picture to tie things together. So basically, we have on the upper corner all the subdivisions into LPFMs of the permutahedron. And here in the bottom corner, basically, the non-negative tropical flag variety can be thought of as these tuples in R14 that satisfy some non-negative conditions, and it have several ways of subdividing it into cones. And in this case, in this cone here, the finest subdivision that we have on top corresponds to a point in one of the cones, and the other finest subdivision corresponds to another point in here in the other cone. And so I just want to thank Chris Eur because he, a few months ago, very kindly provided me with his GitHub code with the non-negative tropical flag variety n = 5. And also Johannes Rau, who is becoming my tropical mentor since I do not do tropical geometry, unfortunately, and my co-authors in these projects. So thank you very much. Thank you for accommodating me. And that's what I wanted to share with you today.
Okay, thank you. Are there any questions? Oh, yeah. Yeah, I will run.
Hola, Carlos. So my question is about the poset. When you see in the positroids as a decoder permutation, there is an easy way to understand the covariant relations. Like, I don't know, this permutation is covered by this one because you transpose these two numbers, or because you change the correlation in a fixed point or something like that.
So that's precisely what we wanted to understand. So let me go back here to the cleaner picture. The general answer, I do not know. And as I said, like, one of the things we did was, so say for instance, you take here the permutation 231. 231 corresponds actually to the uniform of rank 2. And the ones that are below it, each one of them you can obtain by doing a cyclic shift. So some of them we understand via cyclic shifts, and we conjecture that you should always, every time you have a positroid that is quotient of another, the relation among the two permutations should be by a cyclic shift, a certain cyclic shift. We could improve it, but part of that conjecture has been recently proved in this paper of Chen.
Thank you.
Yeah, I had a question. So I had two questions actually, but so first, so in the hypersimplex case, there is a unique finest subdivision into LPMs, right? Into LPM polytopes. And, right? So
there are two. Into LPMs, there is only one, yes.
Yes. So you're sure that this is not the case for flag matroids. So for flag matroids, there are multiple finest subdivisions. Is this true?
That's true, because so here in this picture, already there are two that are finest. And in this paper I referred to in the end, in this paper of Boretsky and Williams, they also have a table illustrating the finest subdivisions of the permutahedron into flags of positroids. In in the particular subdivision of the tropical, non-negative tropical flag variety they are looking at, they have 14 finest subdivisions of the permutahedron. Out of those 14, 2 are into LPFMs. One difference I have noticed between subdivisions into LPFMs and subdivisions into flags of positroids is that it seems to me that when you subdivide into LPFMs, you obtain the smallest number of pieces. That's true with the coarsest and the finest ones so far. But yes, there can be more than one.
Okay, thanks. So
Yeah.
it is true that there are, that was sort of my second question, but you already mentioned it. So it is true that there are finest positroid subdivisions of the hypersimplex in which some of the cells are not LPMs up to isomorphism. Okay, because I mean, so you had the slide where you compared the situations for the permutahedron and for the hypersimplex, and it seemed like the statement for the flag situation for the permutahedron was stronger than for the hypersimplex. So it was.
Yeah. So experimentally, we have noticed that. So say, for instance, for n equal 5, you have subdivisions into pieces, into flags of positroids, where some of them are LPFMs, some of them are not. So you have this mixture. And yes, but yeah, I still don't understand fully the subdivisions of the permutahedron into LPFMs. I also wanted to mention that unlike the case n equal 4, where we know that among the finest subdivisions of the permutahedron, there are some that correspond to LPFMs, I do not know that to be the case for bigger n. So I do not understand yet what are the finest subdivisions of the permutahedron into LPFMs. I understand somehow the coarsest, but not the finest.
Okay, thanks.
Sure.
Okay, is there a question? Maybe one more, just one last question.
Hello, can I ask a few silly questions? So you had that, I guess one of the questions you had at the end were things about F vectors that I realized. Do you have like any like idea about like some like how these like things grow, like analogs of like lower and upper bound results? I guess maybe this is not reasonable because these are F vectors and not H vectors. And do you also know any like have like a nice subfamily where you can characterize what these F vectors are?
No.
Okay.
I do not know. I do
Okay.
not know. And
like how do these grow, or in some sense, I guess?
yeah, no, I
okay.
don't know.
Okay.
And yeah, as I said, I mean, really we started kind of obtaining results on this like very recently. But yeah, that's certainly one of the questions I'm interested on. So maybe we can chat about that.
All right. Thank you. Oh, one last question. Do you know any like interesting algebraic constraints on the properties of the poset?
Any characteristics of the poset?
Like algebraic properties, or like on the topology of the
Yes,
poset?
I do. Yeah.
Okay.
So so here this poset. Here we know, for instance, that for the poset of LPFMs, you can show it has an EL labeling. So yeah, it kind of goes in the direction into computing the Möbius function, but we do that by showing it has an EL labeling.
Okay, thank you.
Sure.
Okay, so due to time limitation, if you have more questions, please ask her directly. So let's thank Caroline again.
Thank you so much.
Okay, thank you.